Hello everyone and welcome to Next Hop. In today's video we're gonna talk about STP and explain it in the simplest way possible. STP is a protocol that prevents network loops while permitting redundancy. Simple as that. Without STP, Ethernet frames would loop around the network, causing broadcast storms, multiple frame copies, and MAC address table instability. The broadcast storm can saturate network with copies of the same frame, causing poor network performance and computer processing unnecessary frames. In 1990s, the IEEE standardized STP in 802.1d standard. But later, as technology improved, we got improved and faster version called Rapid Spanning Tree Protocol with 802.1w standard. Most modern networks use Rapid Spanning Tree Protocol instead of Spanning Tree Protocol. Also, Cisco developed its own STP called PVST Plus and Rapid PVST Plus, which adds STP per VLAN. When STP is enabled, it prevents looping frames by checking each interface before switch sends or receives traffic, either is forwarding or blocking. As we can see here, when STP is enabled, all ports are forwarding except the one port on switch 3, which is in blocking state, and it's preventing a loop in a network. STP does this by electing root bridge, a root port, a designated port which is in forwarding state, and non-designated port which is in other words a blocking state. Now let's explain the root switch election process. The bridge ID exchanging BPDUs call hello messages every 2 seconds. They start bidding with each other, all claiming I'm the root switch. If one switch has the bridge ID priority of 4096, and the others have 8192 and 32768, then the switch with 4096 priority will win the election process and becomes the root switch, because the root switch with the lowest bridge ID priority is the one that wins. The switches always look at the bridge ID with the lowest priority, and then with the lowest MAC address. In this example, all 3 switches have the same bridge ID priority. When a Cisco switch is powered on, the default priority is the bridge ID 32768, which in this case all switches have. Since all the switches are bidding and saying I'm the root switch, then the tiebreaker will be the MAC address. The switch with lowest MAC address is elected as the root switch. In our case, it's switch 1. Once the root switch is elected, there can be only one root switch in the network. No matter if you have 3, 5 or 15 switches, it will always be one root switch in the network. This chart explains port cost, and we must know what's the difference between port cost values to understand STP election process. Port cost calculates the best path from non-root switches to the root switch. For simplicity, most modern networks use 1 gig connections, which is the cost of 4. There are also older 100 megabits links, which is the cost of 19, or faster links like 10 gig, which is the cost of 2. But you get the point. You need to know what's the link speed between the switches in order to calculate the best path. Back to the topology, we can see here that all ports on root switch are always in forwarding state, and we will see an election process of non-root switches electing root ports, designated ports, and non-designated ports. Basically, every non-root switch will have one root port, so when they start bidding, the port with the lowest cost, the root switch, wins the election process. First, we can see here when link from switch 2 goes to the root switch, the cost is 4. But when it goes to the other side, through the switch 3, then the cost will be 4 plus 4, which equals the total cost of 8. Since lower cost wins, in our case it's 4, and it's lower than 8, then this port will be elected as the root port of the switch 2. This also applies to non-root switch 3. When one link from switch 3 goes to the root switch, the cost is 4. But when it goes through the switch 2, then 4 plus 4 equals the total cost of 8. And that's why we have this port elected as the root port, which has the lower cost of 4. There will be some cases where tie occurs, and if the cost is the same, then the lowest bridge ID priority, then the lowest MAC address, and if that ties, is the lowest port number. As we have explained election process of root ports on non-root switches, we also have to see an election process of designated port. As switch 2 and switch 3 are bidding for designated port, the tie occurs with the same cost of 4, then the tie occurs with the same bridge ID priority, and then the lowest MAC address wins, which in our case is switch 2, with the MAC address of all ones we have a designated port. As designated port is elected on switch 2, then all other ports that are neither root port nor designated port, it's put in a blocking state, and that's the final step of STP election process. Before we finish this video, we must mention one more thing, and that is STP Convergence. STP Convergence is a process where switches realize something has changed in a network topology and determine whether to change ports in blocking or forwarding state. If a link between switch 3 and root switch fails, the link between switch 3 and switch 2 will converge, and from blocking state it will go to the forwarding state. First, the switch sends 10 hello messages, which are 2 seconds each, and that's total of 20 seconds. Then it goes to the listening state, which is another 15 seconds. Then to the learning state, which is another 15 seconds. And finally, to the forwarding state. Now, if we calculate this, STP Convergence took about 50 seconds, and that's a lot of downtime in the modern networks. Imagine you are cut off in the middle of your work or a phone call for almost a minute. You wouldn't be happy. As mentioned previously, here steps STP protocol, which is without listening and learning state. STP goes straight from blocking state to forwarding state in a couple of seconds, and that's why STP is mostly used nowadays. And that's it for today's video. If you find it useful, please hit that like button and subscribe to my channel for more content. Let me know in the comment section below if you have any questions. Thanks for watching, and I'll see you on the next one.